Well, first of all, thanks to the organizers first for arranging this conference. It's really nice to be here, and of course for inviting me. Thanks especially to Benoit. The title of my talk, as you see, is Random Quantum Correlations are Generically Non-Classical. It is a joint work with Carlos González-Guillén from Universidad Politécnica in Madrid, Cecilia Lancian and Carlos Palazuelos, and myself from Complutense in Madrid. And it has, last week has been accepted for publication in the Annals Henri Poincaré, that is, I think, edited here. So it's nice to talk about this here. So, yeah, let's start talking. I mean, I'm going to introduce the ideas that I'm going to talk about, and then I will put some notation of, to express the results. I will finally tell the results, and at the end, probably I will sketch the proofs, or, well, some of them even with certain detail, because some of them are easy. What have we known, so in time, about from the foundation's point of view, about non-locality and relation with quantumness? So the most relevant finding probably was the CHSH inequality, or equivalent results, which I think of this as a qualitative result. It says that there are bipartite probability distributions, which are quantum, can be done with quantum resources, and are not classical. They can be not explained with local hidden variable, with any local hidden variable model. And that was, that has been experimentally verified. That got a Nobel Prize once already, and I've seen the loophole that was there, still there, has been recently closed a couple of years ago. So we are now totally sure that there are quantum probability distributions that are not classical. And this we have known for a long time. Then probably one of the next things the community has done afterwards was to turn this qualitative result into a quantitative result. So it's not only that some quantum probability distributions are not classical, but how non-classical they are, how far away from classical they are. And there is a lot now, by now, of results measuring the amount of violation of L inequalities is a way to state it, but somehow how far away those two sets are, the classical distributions and the quantum distributions. And more recently, we are studying what's the probability of non-locality, and I will try to explain this. There have been several, by now, results that consider a random state, or a random quantum channel, or some other random physical objects, and try to quantify or decide whether they are, if they can be simulated with classical resources or other properties. So far away, not much has been, so far, not much has been done just from the foundation's point of view. You consider only the probability distribution, or only the correlation, and you put some randomness there, so some kind of probability distribution, and you have, and then you wonder how likely is it that a random, with whatever randomness you decide to use, quantum correlation is non-local. So now I'm not to look at the physical objects underlying. I will not put the randomness on the states or on the measurement operators, but I'll just put the randomness on the probability distributions, and I measure, and we're going to try to study how likely it is that they are local or they are not. So, yeah, that's what we are going to do in this talk. As it was the case with bipartite probability distributions, like measuring violation of Bell inequality, the first situation we understood was what I call the correlation setting, when you only have two parties, and each party has only two possible answers. I think of them as plus minus one, and you are going to consider the expectation of their product. You could have more parties, you could have more possible answers, but the problem gets more complicated, and we don't know yet how to deal with it. So I will be in the correlation context. That is now the simplest one, and we will begin to understand some things there. Because there are I think, two communities here. Probably, I don't know how much is the operator algebra community, how much of this is trivial or known, or so I'll try to explain things, although a little fast. But So the situation we are in is we have two parties, Alice and Bob, that they are separated. Each of them gets a question, I, j, from a set of questions, 1 to n, here. And each answers plus or minus 1, and we consider what we call the correlation matrix. We imagine we are doing the experiment many times, and we can take an expectation of the product of their answers. This is what we call the correlations for this situation, for this number of questions. I'm going to consider the set of quantum correlations, the set of classical correlations, and I'm going to see how likely it is that a given quantum correlation is classical. Both sets will be convex. I will talk about them in a moment later. So to characterize them, it's enough, or it's very useful to know about their dual objects. So they're separating hyperplanes, or you can think of them, whatever. And they are called XOR games for the computer science community. But for us here, it's just a dual to a correlation. Since correlations are matrices, this is this tau object there. This is just a matrix, an n by n matrix. So a dual object is also a matrix, and the duality is given by trace duality. The duality you put in when you are considering matrix, it coincides exactly with just seeing the object as an object in Rn square and putting the duality. So I will talk about XOR games. That's what they are known for computer science, or for quantum information probably, but it's just the dual. And I will use the value of the game, that is nothing but what is stated there. The quantum value of the game is the supremum of A acting on P when P moves in the quantum correlations, and the classical value of the game is the same supremum when P moves in the classical correlations. So this will witness if something is if I'm going to have something that is classical and not quantum, quantum and not classical, we will witness it with a XOR game. That are also called Bell inequalities, depending on where you are working. So this is just my objects I will work with the taus and the as, the a's there. And before I state our results, I'll say what is known, what was known until now. There are not many results in this direction, so just considering, as I said, not putting the randomness on the physical objects, but just on the mathematical objects there. And there is a first result in this direction, well, that I'm aware of. Okay, the first result in this direction is from 2011 from Ambainis and several collaborators in his group. And they show that if you consider a random XOR game, as I said, this is like a random hyperplane for the space of correlations, a random dual object. Its quantum value is uniformly bigger than the classical value, so is with high probability. So with probability close to 1, when n is large, the value it will attain on the quantum correlations will be extremely bigger than the value it will attain on the classical correlation. It means that for most, in this sense, XOR games, there is an advantage in using quantum resources versus using classical resources. The randomness they put on the games is like the most natural one would put to start with. It's just what is going to be a game. It's a matrix, an n by n matrix, so probably one of the most natural randomness you can put there is just consider each coordinate with separate independent randomness, and you can put there anything that is, for this result, anything that has expectation 0 and variance 1, or bounded variance. So you put normal Gaussians, or you put Bernoullis, and you get this result there. What we are going to study is somehow the pre-dual of this result. So instead of putting now the randomness on the XOR games, I put the randomness on the correlations. And there is no direct implication between any of the two results. So the fact that this happens in the dual does not mean it happens in the pre-dual or vice versa. Yeah, okay. And so we started studying this problem, seeing what happens for the quantum correlations instead of the games. And we started with this a couple of years ago, and in 2015 we proved a first result in this direction, where we prove that with a certain specific probability distribution that was in some sense natural, we could prove that non-locality was generic, so that most quantum correlations were non-classical. But this was like for a very specific randomness that we put. That made sense, but it was somehow restrictive. What we're going to do now, what I'm going to talk about now, is to consider like a quite comprehensive kind of randomness you can put on the quantum correlations, and seeing that the result remains true, so that non-locality is generic. So that's what I do. That's what we will do. And not only that, but we will be able to, the way we will show that something is quantum and not classical is going to be, we're going to give more information, because we're going to be able to estimate what I will call the quantum norm, that it will be nothing but the gamma 2 norm for people in Banach space theory, and the classical norm. Well, the classical norm we will not be able to calculate it, we'll just be able to lower bound it. And the classical norm is nothing but the projective norm in L infinity. I will, in the tensor product of L infinities, I will talk about it later. So we will estimate the norms. We will measure how quantum or how classical is a given correlation matrix, a random correlation, of course in probability, all of this. And from there, these are the fact that there are many quantum non-local things will appear as a corollary. Yeah, so that's what I want to do. And yes, to do this, I start now with the proper definitions. What is a quantum correlation? So it's a correlation that Alice and Bob can achieve using the rules of quantum mechanics. So they share quantum resources, they share entanglement as much as they want, and they have this experiment that I very briefly have shown before. And what is the expression of the probability of the correlations they can achieve? So you just apply the rules of quantum mechanics and you get that there. That the kind of correlations the correlation matrix they can achieve has to be described like the trace of rho, ai, bj, where rho is a state in the tensor product of two Hilbert spaces, and the operators ai and bj are self-adjoint operators on each of the spaces. I will not use this description. That's the one that comes directly from the principles of quantum mechanics. I will use an equivalent description and says that tau is a quantum correlation matrix if and only if can be written like this. And this is mathematically simpler to use, at least for our purposes. And one is just that it can be written at the dot product, at the scalar product of ui's, vj's, where ui's is a set of vectors in a Hilbert space, and vj's is a set of vectors in another Hilbert space. The equivalence between this presentation and the other one is not difficult. One of the implications is very easy. You just write it down and you get it. The other one is a little more elaborate, but is due to Sirelson, I think from '84 or something like this, and it's been known for a long time. It requires Clifford algebras or something equivalent, but it's been known now for a long time. Okay, so this is going to be a quantum correlation. This is what we physically do with quantum resources. And so I'm going to associate to it a natural norm. So I say a matrix is a quantum correlation if and only if can be written like this when ui and vj's are norm 1 vectors. So it's quite natural to consider this norm. There are several notations for this norm. I think I've seen gamma 2 star, omega 2, and omega 2 star for the same object, depending on the authors. But here it will be called the gamma 2 norm. It might not coincide with something that someone else calls gamma 2 norm. And it's the infimum over all the presentations of tau as the product of uv of the maximum norm of the UIs times the maximum norm of the VJs. It means the maximum Hilbertian norm. And well, it can also be seen as a factorization norm. I will not use it. We use it in the paper, but I will not use it in the presentation. But it's very easy to go from one expression to the other. And if you look at what I said before, what was a quantum correlation? Something can be expressed with norm 1 vectors. It's very easy to convince yourselves that tau will be a quantum correlation if and only if the gamma 2 norm of tau is smaller than 1. So I have now the set of quantum correlations described as the unit ball of certain norm in certain tensor space. And this is going to be it's going to be useful for us because it allows us to use tensor norm technology and duality and this kind of norm spaces techniques. In particular, it implies that the quantum correlations are convex because they are the unit ball of a norm. I didn't prove that gamma 2 is a norm, but it's very easy. That's for the quantum correlations. Now, what is a classical correlation, or classical or local? What can Alice and Bob do if they don't have quantum resources? Essentially, they can do convex combination of deterministic strategies. A deterministic strategy will be Alice will always answer whatever when she gets certain question, and Bob will always answer whatever, plus or minus 1, when he gets some question. And that would be, if you make the calculation of that, what is the product? That will be a rank 1 sign matrix. So it will be a matrix of signs of rank 1. And all they can do is convex combinations of this. They can have shared randomness, and they can agree on which strategy how they're going to use the randomness to use the strategies. So they can do convex combination of this, and you come to exactly that, the convex combinations, the convex hull of rank 1 sign matrices. Again, if you look at it and you try to check if there is a norm that goes well with this, you find it fast. That is the projective norm in L∞n, tensor L∞n. You don't need to, if you are familiar with this, perfect. If you are not, you don't need to understand this expression or to know anything special about it. So if you are not familiar with the norm, just carefully skip it. If you are familiar, fine. This describes exactly the classical correlations. And again, it's very easy to see that some correlation is classical if and only if this norm is bounded by 1. This is the infimum when you of the now here x sub x up k, how do you say this? Super k is just a vector in Rn, and you put the infinity norm there. Okay. Yeah. Okay. So you have a norm describing the quantum correlations, and norm describing the classical correlations. Both will be convex objects. It's very easy. I didn't say it, but just considering Hilbert spaces of dimension 1, it's very easy to see that every classical correlation is quantum, which is what we expect. And there are more quantum correlations than classical. That follows from that's what is Bell inequality violations of the CH-SH inequality. So I'm going to need the dual norms, and essentially all I need of them is that they are the duals. So you have the dual, the norm in the dual is just take the supremum of the element of the dual acting on the unit ball of the pre-dual. So that's exactly what it says there. The gamma 2 star norm of a matrix A will be the supremum of A acting on tau, when tau is quantum, and the dual of the classical norm. It is the injective norm in L1n, tensor L1n, but again, you don't need this. So again, if you're familiar with it, fine, might help you follow something. If you're not familiar with it, doesn't matter at all. What is the what is the supremum, what is the maximum value that that XOR game can achieve on local correlations if the local correlations are it's the convex hull of the deterministic strategies. You just have to check what happens in the deterministic strategies. A deterministic strategy is a rank 1 sign vector, so you just have to, or sign matrix, so you just have to check against those. So it's the sup of Aij times alpha I beta j, where alpha and beta are plus minus 1s. This expression I will use later, okay? The fact that this coincides with epsilon norm in L1n, this I don't need it. So, okay, I have I have two norms characterizing the quantum and the classical correlations, and I will use their dual norms. And before I state the results, one more consideration. I'm not going to use Grothendieck's inequality, but it is somehow floating in the air, because I'm trying to separate quantum correlations from classical correlations. And often when you separate things in probability, when you separate things in the asymptotic regime, you get separations in order. Like you have separation of square root of n, and there are constants appearing there, and you don't care about them because they just are washed away by the order. This is not going to be the situation here, because we have Grothendieck's inequality telling us that the quantum and the classical values, the quantum and the classical norm, or the quantum and the classical value of a game, the dual quantum and classical norm, cannot be too far away from each other. They can only be a Grothendieck's constant away. Grothendieck's constant, we still don't know how much it is, but it is somewhere around 1.7, doesn't matter, finite number. So we are not going, we will not have separation in order. So it means our separations will have to be in the constants. It means that we cannot be too rough with the estimates we do, because we only have 1.7 of room to play with. As I said, I'm not using Grothendieck's inequality, just mentioning that it bounds how far away these two norms can be. And, well, I will use, and I think it's going to be useful for the statements of the results, as a basic tool in the proofs, something very basic from linear algebra. There's the singular value decomposition, that if you have a real square matrix, it decomposes as U dv, where U and V are orthogonal, and D is diagonal and positive. The elements of D are called the singular values of A, and the rows of U and the columns of V are the left and right singular vectors. And I'm going to use a result that is, we had to prove it because there was no explicit proof for it, but it is folklore more or less in the area, and it's easy to prove that. So before I state the result, I said that I'm going to apply my results to a large class of random, well, large, I mean, not so a small class of randomness, of random matrices. The class of random matrices I will apply to will be what I will call biorthogonally invariant random matrix, I will mention now. In particular, I wanted to cover the Gaussian matrix. I want to cover a Gaussian matrix. So just where by a Gaussian matrix, I understand in each entry you put an independent normal Gaussian, independent normal 0, 1. Okay? So this is what I will call a Gaussian matrix, and I want a class that includes those. Actually, we did the reasonings for the Gaussians, and then we just understood that everything extends to be orthogonally invariant. But having a Gaussian matrix in mind is like the model we should have. And Gaussians are, a Gaussian matrix is be orthogonally invariant. What does this mean? It means that if you have, since I have here, it just means that if you have your G, that depends on some randomness, omega, if you pick any orthogonal matrix and any other orthogonal matrix, fixed, not dependent on omega, just fix those, and they are orthogonal, okay? And you consider the distribution you get now is also Gaussian, has the same probability distribution. That is being orthogonally invariant, that if you multiply with orthogonal objects from each side, the probability distributions unchanged. So for the orthogonal invariant random matrices, in particular for Gaussians, the following is true. And as I said, this is easy. Distribution is the orthogonal invariant if and only if you consider the singular value decomposition above, and you can split the probability space into the product of three probability spaces, and you can consider a randomness on the first one, on the second one, and on the third one, and so there's a product space, so all those three randomness are independent, and you have that the U and the V will be hard orthogonal, and D may be whatever you want, as long as it is independent of the other. Okay, and this is, as I said, more or less simple. I mean, or as a standard. Okay, this I will use. I still didn't state my results, but now I'm going to. So I'm going to state the results that I prove. I think before you read theorem above, it's better if you read the theorem below, because like the model case, the test case that we have, that is Gaussians, the one above is a generalization. And what it says, if I have a random Gaussian matrix, I put the proper normalization, just that I don't have carry an n then on the expression there, but the normalization, the 1 over square root of n, you can drop it if you want and put it on the other line. Then I can calculate the gamma 2 norm in probability. So with high probability, meaning with probability 1 as n goes to infinity, the gamma 2 norm will be as close as I want to 8 over 3 pi. 8 over 3 pi comes from the Marchenko-Pastur law, that is talks about the distribution of the singular values of a Gaussian matrix. But, okay, whatever that number, but the thing is that I can calculate it. In general, for any random orthogonal invariant distribution, and we will use not only the Gaussian, at least in the paper we have results for distributions that not only for the Gaussian, so the result above is not useless generalization. We do use it. I mean, it has applications. If I have a orthogonal invariant distribution with certain condition on T, on this norm and this norm here, that I will mention now, then I can also calculate the quantum norm. Now, what's the condition there? Seems a little strange, or maybe not. The infinity norm of T is just the operator norm, and is the largest singular value. The one norm in T is the trace norm, and is the sum of the singular values. That means T1 over n is the average of the singular values. What this means is that the largest singular value cannot be too far away from the average. Well, what's the reason for these kind of conditions? That if you want something to be really n by n. Imagine the extreme case. Imagine in the UDV decomposition, imagine the diagonal. You put a 1 on the top, and everything else 0. That will be like very extremely, so this condition will not be fulfilled at all. Of course, if you have 1, everything 0, you put an orthogonal matrix here, and you multiply, you are not having a real n by n matrix. I mean, it's n by n, but the randomness is not n by n. You are essentially killing all the randomness there. So it makes sense that the reasonings do not apply. So some conditions of this kind must be needed. So we call this to have a flat spectrum, but the spectrum is not too uneven. So as I said, in this case, we can calculate the quantum norm. And the thing is, I will not be able to calculate the classical norm, but we will be able to lower bound it. And again, look at the result below. This is the quantum case, and you get 8 over 3 pi. And in the classical case, we get something close to 8 over 3 pi, but not quite. Okay? We have this square root of 16 over 15, that I will tell later where it comes from, which is strictly larger than 1. So they are uniformly separated. They are constantly away from the quantum, I mean in probability. And you get the same result in the orthogonal invariant case. Again, this is the quantum value, you get exactly that same factor. I will show later where it comes from. We don't think that result is tight, so we think they are farther away, but we have not been able to prove it, of course. The good thing about this result is that we not only prove that they are far away, but we show a XOR game, or we show a Bell inequality, witnessing this separation. So we are not only able to say that they are separated, but we give the witness. We say with what game you have to use to prove that they are separated. You can now mix together both results, and essentially what you get is this. That if you have a pure orthogonal invariant distribution with a condition of the spectrum, as I said, think of the Gaussians, the classical norm is always bigger, strictly bigger than the quantum norm. And there are several ways to think of this. So it means if I have a correlation matrix, I divide by the quantum norm. So it is quantum by construction and non-classical with high probability. Another way to think of this is the following. Here I already mentioned what is the Bell inequality. That I consider the set, the space of the correlation matrices, and this is just R over n squared. I'm going to move in the sphere of R over n squared, so and I put the uniform distribution there. So I just put, in the matrices, and I take a random direction uniformly. What our result says is that in most directions that I choose, I will reach the end of the classical correlations before I reach the end of the quantum, the border of the classical correlations, before I reach the border of the quantum correlations, and with constant separation. And moreover, I tell you which Bell inequality will witness this. And the Bell inequality is associated to the singular value decomposition. You have it there, it will appear later. That was surprising for us. So, yeah, that's what. This does not say anything, at least not a priori, not yet, on the relative volume of the classical correlations inside the quantum correlations. There's this kind of problems in convex geometry that things seem to be saying something about the volume, but it actually does not. So, at least not directly. Maybe something can be said, but new reasoning would be necessary. But what it does say, as I say, is that in most directions, when you go to the border of the quantum correlations, you will have something non-classical and constantly away from non-classical. And to prove these results, for the quantum norms, I'll use singular value decomposition. For the classical result, for the classical bound, the tool will be this proposition here, which is not so difficult once one finds the proof, but it's very useful and probably interesting in its own. And it says that we are able to upper bound the dual classical norm of an orthogonal matrix. It's easy to show that this norm will be bounded by n. It's not so easy to prove that in general, and that you can find cases of orthogonal matrices, for example, identity, where the norm is n. It's not so easy to prove that in probability it is strictly smaller than 1. This bound there seems to be tight numerically, so we know it is a bound. We have a lower bound also, but this is something like 0.94. I think we have a lower bound that we can prove that is something like 0.8 something. I forgot now. But numerically, that seems to be that this bound is tight. If it's not tight, it's going to be very close to it, but this we cannot prove. This seems to be tight. I said that the result here, for example here, is probably not tight, and this we believe not to be tight, because we believe that although this is the best number we can get with that Bell inequality, with this UV inequality, or with a UV XOR game, probably there is a better Bell inequality giving more separation, but we have not been able to find it. Okay, so these are our results. And I will say a little about the proofs. When am I supposed to finish?
10
10 minutes, perfect. So I will just sketch a little of the proof. The proofs are not too difficult once one had the right approach, but it really took us some time to get the right approach. Like to use a singular value composition was something we didn't think of, or some things there. But they're somehow reasonable to follow. So although I will go very fast now, but the sketch of the proof is clear. Let's go for the gamma 2 norm. And first I want to upper bound it. So I want to prove that the gamma 2 norm, the quantum norm, is smaller than something. How do I prove that it's smaller than something? So because I look at the norm as this infimum, so I want some decomposition of t equals u times v, u tilde v tilde, so that the ui tilde will be the rows of u tilde, the vj tilde are the columns of v tilde, and I want them to have a small Hilbertian norm, all of them. And the observation is the following. I mean, the singular value decomposition provides one such factorization, and it turns out to be good, because it turns out to be tight. So it is in probability as close as we want to the infimum when n is large enough. What do? We just consider the singular value composition. We have the u, we have the v, and we have the diagonal in the middle. We split it in half. The square root of d goes to u, and the square root of d goes to v tilde. Now, these are the u tilde, these are the v tilde, and now we have to consider the norm of the rows of u tilde and the columns of v tilde. And this is just going to be Levy's lemma. The rows of u are the left singular values, or the right singular values, and they are uniformly distributed in the sphere because the distribution is orthogonal invariant. And what we are putting is, like on a uniformly distributed vector, I'm putting some weight, this multiplying by square root of t, I'm putting some weight on each coordinate. And I have to calculate the norm of that. So you think of the problem and say, okay, this is the standard thing. You consider the mapping, taking a uniform a vector to this norm. This is well calculated with respect to uniform probability. And you calculate the Lipschitz constant of that, and you apply Levy's lemma. And you plug in the machinery, you have some calculations there, and you get it. Okay? You get the probability of this norm being large is exponentially small. You need this to happen for a linear number of vectors, m vectors, that will still be very small, still be exponentially small. You need the proper relation between the average and the Lipschitz constant. And this relation between the average and the Lipschitz constant is exactly the condition of this flat spectrum condition, this d1 over n being not too far away from the infinity. And it's just, as I said, apply Levy's lemma and do the calculations. The other inequality, it is easier. So the surprising thing is that, I mean, it's like this is not difficult, and somehow the surprising for us thing was that is the good one, that this decomposition is good enough. How do you see it? The other inequality is easy. I mean, just Cauchy-Schwarz will do. But I will present another proof, different, that is also very fast, because it's the one I'm going to have in mind for the classical bound. So, as I said, you can prove it just using Cauchy-Schwarz, and just try to write something and you will get it. And what else can we do? I need to see that the some norm is large, so I use just duality. What you usually see is that t acting on O is going to be smaller than gamma 2 of t times gamma 2 dual of O. This is just duality. And you reverse the inequality, and so what do you want now? You want now, so gamma 2 of t is going to be bigger than t acting on a XOR game, on a Bell functional, divided by the gamma 2 star norm of this Bell functional. And the observation is that if you use as Bell functional or as a XOR game exactly uv, what do you get? So t is udv, then you put uv transpose and you take the trace, and you just, only d survives. So you get the trace of d, there is t1 on n. And to check that the gamma 2 that the gamma 2 star norm of O is n. That's immediate, and that is not probabilistic, that is always n. Why do I write this proof? Because this is what I'm going to do now for the classical case. The classical result is more difficult to prove, and we only lower bound it. We don't know the upper bound, and we don't think our lower bound is tight. So it's more difficult, at least for us. But we are going to, the bound we are getting it from exactly this diagram. Now replace gamma 2 by the classical norm and gamma 2 star by the dual classical. And I'm going to use the same Bell inequality, UV. It's going to be the same O. That means the numerators are going to be exactly the same. And now what do I need? I need to prove that the denominator is smaller than something. That the gamma 2 star of O is not too large. How will we do this? So, as I said, I want to see this. And this is the union bound and area of spherical cups. So we actually think by now we have 3 proofs of this fact, because the first one we thought was way too complicated, and then, but also thanks to the referee who suggested several improvements, at the end, the proof we have is quite simple, yeah? Quite reasonable. What are you going to do? We have to calculate this supremum, so I can at least say the lines of the proof. I want to calculate the supremum on alpha I, beta g's being plus minus 1. What I'm going to do is that for one given choice of alpha and beta, the probability that that is large is very small enough that if I apply the union bound over 2 to the 2n choices of alpha beta, that still remains small. Okay, so this is what I have to do. And well, if you start drawing pictures and so, I'm not so good drawing pictures with latex at all, so not even with my hand. So, but the reasonings are more or less, I mean, they're easy to follow. What I'm thinking that I'm fixing alpha and beta. So first, forget about beta, fix an alpha, and consider the vector O acting on alpha. That is the vector you have there. This is phi. Just normalize. I have to normalize the norm 1 version of alpha. And this is a random vector because O is random. It is norm 1 because O is an isometry and 1 over square root of n of alpha is norm 1. And because O is higher distributed, phi is uniformly distributed in the sphere. So this is a uniformly distributed random unit vector in Rn, uniformly distributed vector in the sphere. I want to play this vector now against beta, because the number I'm trying to bound, which is this, is nothing but the dot product of, well, I have a constant dilating phi, but phi times beta. Because phi is totally random, and beta is a sign vector, I may as well consider beta is all ones, because the randomness of phi tells me that it's equivalent which beta I consider. So I consider just that beta is all ones. And now I want to check the probability that the dot product of 2 vectors is large. So this is just more or less simple calculation. The dot product is related to the cosine. So the probability that this product is larger than a cosine will be the probability that the vector is in the cone defined by, I have the vector beta and I have the spherical cap. So the cone intersecting the sphere, and I just want to see the relative size of the spherical cap. What is the size of this spherical cap compared to the size of the sphere? And this is a calculation. It's been used in more places, and there are estimates for that. We got this estimate from the recent book by Sarek and Obrun, this Alice and Bob Banach, something like this, sorry, forgot it. And that is very nice, the book. And well, the calculation, we took it directly from the estimation, we took it directly from there, and now you just, what you are saying is that for a given alpha beta, you're showing that the probability of this product being large is smaller than something. And now you have 2 to the 2n choices for alpha beta, and you apply the union bound and fine-tune the constant there. They've got the constants appearing, you just have to tune them, and we get this number. The proof is not awfully complicated. So we didn't think at all that it was tight. But then we did numerics, and it does, I mean, we were trying to improve it, we couldn't, and it does seem to be tight. But we've not been able to prove that it's also a lower one. And yeah, I think that's all I wanted to say. I think
okay.
When you do SVD, you only take square matrices?
Yes, this is all we are doing for square matrices.
What are usually, can they be unitary, or
Sorry?
some property on U and V? Are there some properties?
Well, because my matrix is, I'm considering be orthogonally invariant. A result I put there before says that U and V will be hard distributed. They are orthogonal, and they will be hard distributed in the orthogonal group.
So more questions?
Did you look into 3-player vector games or more?
Yes.
What?
Yes.
Okay.
Well, no result. You don't have a SVD decomposition anymore. And it wasn't obvious that that was going to be a good tool, but once we found it, it was a very powerful tool. Yes, we look to no avail yet. And yes.